Okay. So let me switch back so you guys can see the whole thing. You see it?
Mm-hmm.
There it goes. Okay.
You should just go really fast.
All right, so what we're going to do here is we're trying to find the horizontal displacement at C. So there's our our real system, and as we've mentioned just before, I went ahead and penciled in where I think my virtual system's going to be. So what we need to do first is find our moments for the real forces. So I'm going to make a cut in the first system, AB. Let's just say I make a cut here. I'm going to work the right-hand side. It looks more complicated, but I don't want to have to find my reactions. So let's start with that. Let's see. I'll draw that free body diagram on this section. So this will be section AB. And let's draw the free body diagram for that. So I'll have something that looks like this. So on the right-hand side here, I'll have the concentrated equivalent force, which will be equal to 200 pounds per foot times 8 feet. That's 1,600 pounds, right? Or 1.6 kips. And that's located in the middle, 4 feet, 4 feet. I didn't give myself enough room up here. I'm sorry about this. So I'll have another concentrated equivalent force for this section. Also, let me switch colors here just to make it easier to see. I'm going to be measuring my moment in this direction. I'll call that x1. So here's my interior moment, the moment in AB, as a function of x1. Now what's this force going to be that I've created here? What's 400 pounds? Oh, I'm doing kips. I shouldn't have done kips, but I've already gone that way. So it'll be 0.4 kips times x1, right? That's the concentrated equivalent. I forgot to sketch that in. I'm sorry about that. And of course, the distance to the centroid is half the distance, or x1 over 2. So if I do my equilibrium, right-hand rule, summing moments about the cut, making sure they're in equilibrium, starting with my moment, that's a negative moment, so I have the moment in AB. This creates negative moment. The force is 0.4 x1 times a moment arm of x1 over 2. And then this is also negative. 1.6 times a moment arm, that's kips by the way, times a moment arm of 4. So I should be able to find my moment in AB should be equal to all that stuff. So what do I get? I get negative 0.2 x1 squared minus, what is that, 6.4?
Yeah.
6.4. Bless you. And that should all have the units of kip feet. So a quadratic moment expression. So now let's go to the next section. And this will be section BC. So I'm going to cut it here in BC, and I think it's going to be easier to look at the bottom section. So I'll draw a free body diagram for that. This time, unlike up here, unlike up here, I'll go ahead and sketch in kind of the distributed load that we know is there. and I will assume that section varies from 0 at the tip up, and we'll call that y. And then I'll assume a positive bending moment in this direction. And then the concentrated equivalent of that distributed load will be the load, which is 200 pounds per foot times a distance of y. So we're doing in kips, so that'll be 0.2 kips times y. And of course that'll be y over 2 distance from the end. So now when I sum moments about the cut and put it in equilibrium, this will be a negative moment, the moment in BC, and this will also be negative. So the force is 0.2y, and the moment arm is y over 2. So it looks like my moment in BC is negative 0.1 y squared. So far, so good?
Yep.
Okay, so let's redo that for the virtual system. So we'll eliminate all the applied loads, and now we'll come back to our virtual force here. And we're going to do the same section. So coming back and looking at our virtual forces. Okay. We'll start again with section AB, and I will draw the same rough free body diagram, except this time the only force on the system is the virtual force, and I'll have the virtual moment in AB. And it will still be a function as before, because once you set that system, you can't change it. So this will also be x1. This total distance here is 8 feet. So now when I sum moments using right-hand rule at my cut section, make sure they're in equilibrium. What do I have? Well, I've got my internal moment, which is negative, and this virtual force of 1 also creates negative moment with a moment arm of 8 feet. So it looks like the virtual moment in AB is simply just negative 8. And it has these weird units, right? Just kind of feet. Because we're assuming the virtual force is dimensionless. Okay? And now we'll look at section BC. The free body diagram for that is just a lower section. Again, we have our virtual load of 1. And just as we defined previously, that will vary as we move up y, and I assumed a moment in this direction, so I'll assume a moment in the same direction, except this is the virtual moment. Let me slide that up a little bit so I can see it a little better. So now when I sum my moments about this cut that I've made, make sure it's in equilibrium, I have the virtual moment BC, it's negative in my sign convention, and then so is the virtual force at a distance of y. So it looks like my virtual moment BC is just minus y. And again, has that strange unit of feet, the way we're working it. So what do? Match them together and integrate, right? So I'm going to slide that off the top for a little bit, so we'll have a fresh sheet. So now we know that the displacement at C in the horizontal direction is going to be equal to, first I'll factor out my E and I in the denominator. They're constant for both these problems. And starting with section AB, I'll integrate over that length with this from 0 to 10, the real moment in AB times the virtual moment in AB. And I chose a variable for that. I think it was x1, so this will be dx1. Then I'll add the bending energy in section BC, which goes from 0 to 8. And I'll get the real moment in BC, virtual moment in BC. In that case, I chose, you can see it here, I chose y as my variable, so we'll integrate that dy. So there's the general virtual work expression. So for this particular problem, we'll just plug in our values and see what we get. So the first integral from 0 to 10, the real moment in AB was negative 0.2 x1 squared minus 6.4. And the virtual, you can barely see it here, it was negative 8, I believe.
So if you left this in pounds, your answer will be different, right?
Right. But the unit of your final answer will be pounds. So the only difference here will be 1,000. We'll be off by 1,000.
That's my fault.
So my answer is in kips. If you do it in pounds, you'll just be 1,000 times more than me. But remember, E is in kips, so eventually it'll all work out because we'll have to get the units back square. And then finally, from 0 to 8, the real moment was equal to negative 0.1 y squared, and the virtual moment was negative y. So there it is. I'm wondering, should I venture to try to solve this problem? No, I don't think so either. I think at this point you could probably... It's not incredibly hard. I mean, you just multiply that 8 through. This is going to be 1.6. So it'll be x1 cubed, 1.6 divided by 3. You can see the fractions are going to get kind of... I'll tell you what I'll do is I'll finish this problem and get an answer, and I'll publish it on the website. I'll scan this. I won't do a video, but I'll scan it. Now for the exam, in most cases, let me see if I can kind of get all this nearly on the slide. For the video, for the exam, I'll in many cases I'll just say this is enough, right? If you can build the real moments, the virtual moments, and construct what I'm going to call the virtual work equation to this point, that's good enough for me. I may then give you some bonus points if you have the time to actually finish the integration and produce an answer. Of course, in homework you have lots of time, so it's good to go. Okay, so I'll finish this up at my desk later, and I'll publish it in a hard copy online.